Have you ever wondered about the man behind the apple? Sir Isaac Newton wasn't just a scientist, he was a physicist, mathematician, and more. Born on Christmas Day in the year 1642 in a small English village, Newton's life was anything but ordinary. Orphaned at a young age, he was raised by his grandmother, and from early on, his intellectual curiosity was evident. His journey into the world of academia began at Cambridge University, where he initially studied law. However, it was during his time here that Newton developed a deep fascination for mathematics and physics. This led to his early achievements, such as his groundbreaking work on the binomial theorem, his development of calculus, and his theories on color. From a small farm in Woolsthorpe, Lincolnshire, Newton's insatiable curiosity and relentless pursuit of knowledge propelled him into a world of scientific exploration and discovery. From humble beginnings, Newton began a journey that would revolutionize our understanding of the universe. Newton's laws of motion are fundamental to our understanding of physics. But what are they exactly? Well, let's begin with the first law, also known as the law of inertia. It states that an object at rest stays at rest, and an object in motion continues in motion, unless acted upon by an external force. Think about a soccer ball. It won't move until you kick it, and it won't stop until something interferes with its path. Next, we have the second law, which tells us that the force acting on an object is equal to its mass times its acceleration. In simpler terms, the heavier the object, the more force you need to move it. Finally, we have the third law, which you might know as, for every action, there's an equal and opposite reaction. This means that any force exerted on a body will create a force of equal magnitude, but in the opposite direction on the object that exerted the first force. These laws remain the cornerstone of classical physics, even centuries after Newton's time. Gravity, a force we experience every day. But it was Newton who first quantified this force in his law of universal gravitation. Picture this, an invisible string, pulling objects towards each other. This is essentially the concept of Newton's law of universal gravitation. It states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses, and inversely proportional to the square of the distance between their centers. Quite a mouthful, isn't it? But in simpler terms, it means that the larger the objects and the closer they are to each other, the stronger the gravitational pull. This law was revolutionary. It provided an explanation for the motion of celestial bodies, from the tides on Earth influenced by the moon, to the orbit of planets around the sun. From apples falling from trees to the orbits of the planets, Newton's law of universal gravitation explained it all. Newton's contributions weren't limited to physics. He also made significant strides in the field of optics. In the late 17th century, Newton embarked on a series of experiments with light, which would forever change our understanding of color and vision. One of his most famous experiments involved a simple prism. Newton shone a beam of sunlight through the prism and observed a spectrum of colors on the other side. This was contrary to the popular belief of his time that light was colorless, and colors were produced by mixing light with darkness. Newton argued that white light was actually a mixture of many different types of rays, which were refracted at slightly different angles, and each different type of ray created a different spectrum color. This revolutionary theory of color laid the groundwork for the field of spectroscopy. Newton's work in optics changed how we understand light and color, laying the groundwork for future discoveries. Newton wasn't just a physicist, he was also a mathematician. His contributions to mathematics are still used today. Among his most significant contributions is his work in calculus. Newton developed the fundamentals of modern calculus concurrently with Gottfried Leibniz, another brilliant mind of the 17th century. His version of calculus, known as fluxions, laid the groundwork for the mathematical study of change, allowing us to understand and predict the behavior of constantly changing quantities. But Newton's mathematical genius didn't stop there. He also played a pivotal role in the development of mathematical notation. He introduced the familiar dot notation to represent derivatives, a core concept in calculus. This notation simplified mathematical expressions and paved the way for more complex equations. Newton's mathematical principles have become so ingrained in our mathematical understanding that we often take them for granted. But every time we solve a calculus problem or use mathematical notation, we're standing on the shoulders of this giant. From calculus to mathematical notation, Newton's contributions to mathematics have stood the test of time. Newton was a man of many talents, including philosophy. His philosophical views shaped his scientific pursuits. Delving into his philosophical notions, Newton had a unique perspective on space and time. He proposed the concept of absolute space, which exists independently of any material body or physical event. This space, according to him, was immovable, providing a universal frame of reference. As for time, Newton saw it as an absolute entity that runs uniformly, unaffected by the happenings of the universe. It's an ever-advancing clock, ticking at the same pace everywhere. Now, when it came to the nature of the universe, Newton's philosophy was deeply intertwined with his scientific ideas. He saw the universe as a vast, orderly system, a clockwork mechanism governed by laws of physics. His philosophical views, thus, laid the groundwork for his scientific theories and continue to shape the way we perceive our physical world. Newton's philosophical views continue to influence our understanding of the universe and our place within it. Did you know that Newton was fascinated by alchemy? This interest influenced his scientific work. While today we might think of alchemy as a misguided attempt to turn base metals into gold, it was a serious and respected field in Newton's time. In fact, Newton saw no boundary between his alchemical research and his mathematical and scientific work. He spent countless hours poring over alchemical texts, conducting experiments, and even writing his own treatises on the subject. Alchemy, with its focus on transformation and purification, offered Newton a framework for understanding the physical world in a way that complemented his scientific pursuits. For instance, his alchemical studies led him to theories about gravity and motion. He viewed the universe as a grand alchemical experiment, with forces acting upon matter to create change and movement. Despite its reputation, alchemy played a significant role in Newton's scientific discoveries. Newton's Principia Mathematica is one of the most influential works in the history of science. This masterpiece, officially titled Mathematical Principles of Natural Philosophy, is where Newton formulated the laws of motion and universal gravitation, forming the bedrock for classical physics. It's not just a book, but a monument to human intellect and curiosity. Principia was revolutionary in its time, propelling the scientific community into a new era. With it, Newton gave us the tools to predict the motion of celestial bodies and understand the physical laws governing our universe. The principles laid out in Principia remain relevant today, still taught in our classrooms and used by scientists around the globe. It's a testament to Newton's genius that a work he penned over 300 years ago remains a cornerstone of scientific understanding. Principia Mathematica remains a testament to Newton's genius and his profound impact on science. Newton's life was extraordinary, but his legacy is even more impressive. This statement encapsulates the monumental impact of a man who fundamentally transformed our understanding of the universe. Sir Isaac Newton's work has permeated various fields, from physics and mathematics to astronomy and philosophy. In the realm of physics, Newton's three laws of motion and his law of universal gravitation are foundational. They are the bedrock on which classical physics was built. They've helped us understand everything from the trajectory of a thrown baseball to the orbit of the moon around the Earth. To this day, these laws are taught in classrooms worldwide, forming the first steps in any budding physicist's journey. Beyond physics, Newton's work in calculus has had a profound impact on mathematics. His development of mathematical notation and principles has allowed for the expression of complex mathematical concepts in a clear, concise manner. Even now, his notation and principles are used by mathematicians and engineers across the globe. In the field of astronomy, Newton's law of universal gravitation was groundbreaking. This law, stating that every particle of matter in the universe attracts every other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them, revolutionized our understanding of celestial motion. It enabled us to predict the movement of celestial bodies and understand the cosmic dance that unfolds in the night sky. Finally, Newton's philosophical views, particularly his ideas on space, time, and the nature of the universe, have significantly influenced philosophical thought. They've sparked countless debates, challenging and expanding our perception of reality. In conclusion, the influence of Sir Isaac Newton's work is immeasurable. His discoveries and theories have shaped centuries of scientific and philosophical thought, and they continue to do so. His legacy is a testament to the power of curiosity and the human capacity for understanding. From his laws of motion to his law of universal gravitation, Newton's legacy continues to shape our understanding of the universe.